Right, so in this lecture, we're going to be continuing to look at graphs. And this week, specifically, we're going to be exploring ways of finding paths through a graph. We're going to take a look at two algorithms which can generate the shortest path between two vertices within a graph. The first algorithm that we're going to take a look at is Dijkstra's algorithm, which is named after the Dutch computer scientist Edgar Dijkstra. The original algorithm was published in the 1950s, but over the years it's been improved in efficiency, but still remains heavily used today to work out the shortest path between two vertices, as well as the shortest path to visit all of the vertices within a graph. So let's take a look at how it works. We're going to visualize how Dijkstra's algorithm works by color coding the vertices in the graph. We're going to use the color yellow to represent the vertex that the algorithm is currently looking at, and then the color green will represent vertices that have not yet been visited, and the color red will represent vertices that have been visited. And we're also going to display labels by each node to indicate the cumulative cost of reaching them from the origin node. So above each node you'll see a label there with a number inside it. Right, so this is the graph that we're going to be using for our example. And you can see that we have 6 vertices labeled from A to F. It's a directed graph, as you can see by the arrows. And you'll also see the numbers assigned to the edges. And remember from last week, this is the weighting. This is the cost of how long it will take to get between the vertices in the graph. Okay, so we're going to be using Dijkstra's algorithm to find the shortest distance between nodes A and F. And so the first step of Dijkstra's algorithm is to set all of the vertices to be unvisited and all the distances to the vertices to be null. And then the next step is to set the origin vertex to be the current vertex and the distance to this vertex to be 0. And this is vertex A in this example. And then the third step of Dijkstra's algorithm is to update the distances for all of the vertices adjacent to the current vertex, which is A, remember. And the calculation for this is the current vertex distance plus the value of the edge. So you can see that from A to B, that's a cost of 2. So therefore 0 plus 2 is 2. So we update the label above B to have the value of 2. And from A to C, that has a weighting of 4. So 0 plus 4 is 4. So therefore, we update the label above C to have the value of 4. And then the fourth step of the algorithm is to set the current vertex to the adjacent vertex, which has the lowest distance attributed to it in the label. So in this case, because A to B is shorter than A to C, we set B to be the current vertex. And then from there, the algorithm repeats steps 3 and 4. So repeating step 3, we would look at the edges from vertex B, which are to C, D, and E here, and then we would update the distances in the labels above these vertices. And you'll actually notice that we update the label of C from 4 to 3, because we can actually get to C faster going through B, because it's 2 from A to B and then 1 from B to C, rather than going from A to C directly, which has the cost of 4. So we do the same process for the other vertices, D and E. And then once we've done this, we then go to step 4, which we update the current vertex to the next lowest, which is C in this case, because that has the value of 3. And then we look at the edges from C. It only has 1 from C to E with the weighting of 3. And in this case, we don't actually update the label above E, because remember that Dijkstra's algorithm only wants to keep a track of the shortest path to these vertices. And in this case, the shortest path is from A to B, which is 2, and then from B to E, which is also 2. So that makes 4 in total. Okay, so that's why we maintain the value of 4 above E rather than updating it to 7. And so then we repeat step 4, which is to update the current vertex to the next lowest. And that's going to be E in this case, from C, from 3 to 4. Okay, so from there, we then go back and repeat the algorithm again. And so we look at the edges from E, which are to D and F in this case. And then, of course, we find the shortest distances to these vertices and update the labels accordingly. And then once we've updated these labels, we then go to the next lowest vertex, which is D, and check its edge, which only has one edge from D to F. And as there is no quicker route to get to F, we don't have to update the label above F. Okay, and then finally, as F is the last node to be visited, we then complete the algorithm by going to that last unvisited node. And as that has no edges, we then finish the algorithm. And so Dijkstra's algorithm has successfully worked out the quickest path to each of the vertices in the graph. And we can also then backtrack the quickest path between two vertices through the labels assigned to each of the vertices in the graph. And so here you can see that the quickest path from A to F is to go through B and then to E and then to F. And it's worth saying that this procedure can be applied to any two vertices within the graph. Okay, so here's the pseudocode for Dijkstra's algorithm. And in fact, I think we'll transition here to the implementation part. We'll have a look at explaining this algorithm further and then implementing it. Okay, so let's have a go at the first few exercises where we implement Dijkstra's algorithm. Okay, and as always, I'll get you started. Right then, let's implement Dijkstra's algorithm. Okay, so we're going to start by using some of the code which we wrote last week. So if you copy the graph class from last week, as well as the location class and the priority queue into this week, or if you didn't manage to complete last week, don't worry, you can get these files from Blackboard. Under here, you can download all of these and include them, either in the project from last week, or I've created a new project this time just to keep the two weeks separate. Okay, and you're also going to need the linked list class, the template version of it. Let's show you that. I recommend also downloading it from Blackboard as well because we've modified it to work with graphs. Okay, it's got some extra methods and some modded methods. All right, so that, and also the stack class as well, the template version of that. And again, recommend using the version on Blackboard because again, there's some modifications to make it work with graphs. Okay, so it's those 5 classes we're going to start with. All right, and I've also copied in the graph that we used from last week, although we're actually going to be using a different graph. This at least gives us a start, and we can save a little bit of time here, but we'll come back to that a bit later when we've added in the class for Dijkstra, as well as the other node class that we're going to be using. Okay, so now that we've got set up then, let's proceed and have a look at the modifications we're going to have to make. So the first thing we're going to have to do is modify the graph class that we wrote last week. We're going to add in some additional methods to make it work with Dijkstra's algorithm. Okay, we're going to, the first method we're provided with is a get JSON vertices that works with a linked list rather than the priority queue. Okay, so let's add that in. I'm going to go to my graph header file, and I'm going to copy this in to the bottom of it. Okay, and it's written for the CPP file, so I'll just take the scope resolution operator out to get it to work with the header only. Okay, so that's the get adjacent vertices with the linked list. All right, then we're going to need a method to return the distance between vertices. Okay, that's going to get the data from the adjacency matrix and return that so it can be used. Okay, and then finally, we're also going to have a method which will return the lowest weight from the adjacency matrix. Okay, So let's add that in as well. Okay, and we're going to be calling these methods from our Dijkstra class so that we can perform the algorithm. Okay, so that's that bit. Then next, we're instructed to create a node wrapper class. Okay, so this is going to wrap around the location class that we used last week to resemble the vertices within our graph. We're actually going to we're actually creating a new class this time. We're still keeping location, but we're going to create an extension of it, basically, which has a G value. Okay, that's the lowest cumulative weight, or if you like, the cost of reaching a particular vertex from the start. It's the label, if you remember from the illustration. Okay, each node's going to have a label. All right, that's how we're going to resemble it. Okay, and then of course we've got the pointers to the location, and we've set up next pointers as well as parent pointers. All right, so I think I've got the template for this class. I've added that already. Again, just to save time. Okay, so walk through the attributes. Let's look at the methods then, and I think we're given a description of what to do. Okay, so let's start here. We're told to assign the parameter to the corresponding class variable within the constructor. So let's do that. Let's say that the class variable location pointer is going to take on the address of the parameter pointer. Okay, and then we just initialize parent to be 0, as well as G to start at 0. Okay, if you remember, that's the first step. We assign all the labels to be 0. Okay, when we start the algorithm. All right, and then we've got some overloaded methods here, and since we're going to be wrapping the location within this node, we actually need to compare the locations, which will then call the overloaded methods within the location class, because if you remember, that's what we set up last time. Okay, so we're going to be doing something similar here for this. All right, so we can just say that if this location is not equal to right hand's location, return true, else return false. Okay, and then we can say a very similar thing for the equality operator. We just have to change the sign. All right, so that should complete the node class there. The only thing to note really is that they're all public, okay, because we're going to need to get access to these particular pointers and the G value. So keep the attributes public as well here, okay. Unless you want to make them private and then create getters for them, that might be the way to keep in the OO convention. But just to get this working, we'll try and make it as easy as possible. So from there then, let's move on. I've just implemented the node class. Let's go on and look at the Dijkstra class. Okay, so I've set up a template just to prevent this video from getting too long and saving us time here. So walk you through the attributes. We've got a pointer to the graph. Okay, that's just going to pass that in from the main. And then we're going to remember we've maintained two lists. We're going to maintain an open list, which here is going to be the link list. All right, and then we're also going to maintain the shortest path as we go. Okay, so that's going to be a stack in this time. Okay, and if you notice any naming differences, well, they don't have to be this, but just make sure that if they're different, that you adjust them. Okay, I'll try and point out differences as we go. Okay, and then we've got the constructor for Dijkstra, which will do that assigns the graph pointer. Let's do that. Okay, and then we're also instantiating the link list. So let's set that up. Let's say open equals new linked list. All right, and remember we're going to want to store nodes here. So make sure that you put that there. All right, so that's the constructor. Okay, and then we're actually given the code for the reconstruct plan and the find lowest node. So if you scroll down below, you'll find that we're given the code for that. So feel free to copy this in. So save you time having to write them out. All right, so I'm just going to replace these with this. Okay, and as I said about the name differences, so here stack is going to have to become stack2 to work with the particular class name that I've got. But if you've got a different class name, feel free to adjust it to that. Or if yours is called stack, feel free to leave it as stack. Okay, and I think the rest is all right there. So from here is where we get to the challenging bits. We have to implement the GetPath algorithm, which if you remember from the slides, we're given the pseudocode for this. And I've just copied it in from the PowerPoint presentation, which is here. I've just copied it in from there, and I've popped it in Word so we can see it side by side. All right, and again, some of these lines are a little bit cryptic, so we'll try our best to try and demystify them for you. All right, so let's walk it through. First line is where we're supposed to wrap the start and goal in nodes. Okay, so for this particular method, we're given two location pointers to the starting vertex and the goal vertex, if you remember. And we're supposed to wrap these in nodes. So we need to create a node here for this. Let's say start node equals new node, and then we'll pass it start there to the constructor. Okay, and then exactly the same thing, but for the goal node. So let's say that's goal, and then pass it goal from the parameter. All right, so that line's going to break down into two separate lines of code there. Okay, and then the next line, we're told to insert the start node into the open list. And if you remember, open is our linked list. It's going to maintain the list of nodes that we haven't yet visited. So we want to call the insert method, and we want to pass the start node to that. Okay, and then next we're opening a loop. So we say while open is not empty. So remember, we can call the isEmpty method, and whilst that's false, let's open the loop up there. Okay, so we want to set current to the lowest node in open. Okay, so we've actually got a method which will find the lowest. All right, and that belongs here. Okay, so we can call this, we can say find lowest node. Okay, and that's going to take in a linked list, as you can see. So we pass that open. Okay, so then that returns a node. So we want to return that and store it in current. So we need to then set up a node pointer for current to assign it. Okay, so a little bit complex there, but I hope that managed to break it down for you. All right, and then we want to remove current from open. Okay, so if we call the delete method from open, that should remove it. And remember, this delete method, it's going to search through the linked list, looking for a match, and then once it finds it, it will then remove it from the list. It will reassign the pointer. If you remember back to linked lists, it assigns it to the next pointer of the one it wants to delete, just so that we don't lose the end of the list. Okay, so that's that bit. And then next, let's have a look here. So next bit, we've got to store current adjacent vertices in an adjacent linked list. Okay, let's break this down. So let's first of all create a linked list and I call it adjacent. So let's say linked list. And we're going to want to create this linked list of the location class. Okay, and then we'll give it a name. Let's call it adjacent vertex, short for vertices. Oh god, let's type the whole thing. Adjacent vertices, right? And then we've actually got a method that we can call to get the adjacent vertices. Remember, we added this into the graph earlier. If you were to go back to the graph class, you would see we've got a linked list version of get adjacent vertices. So we want to call that. Oops, let's go back here. So we want to say graph and then get adjacent vertices LL. All right, and that's going to take a vertex and we want to pass that current. All right, and we're actually going to have to be specific. We're going to have to pass it the location of current. All right. Okay, and then finish the line. Right, so that was that's quite a lot going on there for that particular line, but that should store the adjacent vertices in a new adjacent vertices linked list, something we can use here. Okay, and then now we're creating a new loop. So we're going to say while adjacent, presume that's adjacent vertices, is not empty. So let's say adjacent vertices, call the isEmpty methods. It's false. Open that loop up. Yeah, okay. And then next, within that loop, we want to create a new edge node. Well, actually specific, this is going to be an edge location, and then next time we're going to wrap it within a node. And let's then assign this edge location the lowest weighted in the adjacency list. Okay, so first of all, let's set up this edge location. All right, and remember, we've also got a method for this. It also exists in the graph class. There we go. We've got get lowest weight, which we can call. So let's do that. Let's say graph get lowest weight. Okay, that's going to take two parameters. That's going to take the linked list. Okay, so we'll pass that the adjacent vertices linked list, and then also the current vertex. All right, and again, we're going to have to be specific. We have to give it the location there. All right, and then is when we want to wrap that edge in a node. So we will say next line node edge node equals new node edge. Okay, and then next, what's the next line? We need to set the distance to the current G's value plus distance between current and edge. Okay, so let's set up a variable, first of all, for distance. Okay, then we want to assign it current G plus distance between current and edge. Aha, and remember, we've also got a method for this. Distance between should be the third method that we added. Oh, there we go. Yeah, distance between vertices. Okay, so we want to call this from within here. So we have to do that through the graph pointer. Graph, and then distance between vertices. All right, and that's going to take the two locations. So we need to pass it current. Oh, so we need to pass it current location, and then also edge. And a point to note that we want to pass it the location version of adjacent. There's no overload yet to use the node version of it. Okay, so pass the location version of edge there. And then let's go on to the next line. All right, so next we're saying if edge nodes G is 0 or distance is less than edge nodes G. All right, so let's break this down. If edge node, referring to the node version of edge this time, G is 0 or distance is less than edge node G. Okay, yeah. And then within here, we want to set edge nodes G to be distance. And then next we need to set edge nodes parents to currents. Okay, so this must be where we are moving on. After we've done this, process this node, we're going to update the parents, move on to the next one. Okay, and then next we've got a separate if statement. We're going to say if edge is goal, so we want to say if edge nodes location has the same value as the goal location, because remember they're both location pointers. If that's the case, we will then want to return the reconstruct plan from, this is from the Dijkstra algorithm. This is here. So we call that and we pass it edge node. Okay, let's put a semicolon there. And if, how are we doing? We've got a few more bits. And then after we've processed that if statement, we want to say open insert edge nodes into the open list. Okay, that should be that. And then we want to delete edge from the adjacency list. Okay, so this must be referring to the adjacent vertices list that we created earlier. We'll say adjacent vertices, delete, passing it location. So we want to pass it the location version of edge rather than the node version of edge. Okay, and then end loop, and then finally return 0. Okay, so hopefully if we've coded that correctly, that should work out our path, our shortest path between the start and end node. So let's put this to the test then by testing it out for this new graph that we're given here. Okay, so what we'll do is we'll go back to the main. And where I copied in the graph from the previous week, we're going to modify some of this. So you notice here that we've got 6 vertices within our graph. So I want to update this from 9 to 6. And I only need up to F this time. So I'm going to go from 0 to F. And actually, whilst we're here, remember last time when we created a pointer for the start vertex, we actually want to do the same thing here so that we've got a handle to then send to Dijkstra's algorithm for the goal vertex. Okay, so what we'll do is we'll say end vert, and then we'll put the F vertex into that. Okay, and then of course we'll still add it to the graph, but it just gives us a handle then to send those two to the Dijkstra's GetPath, because remember that needs a start and an end. All right, so that's what we're going to do there. And then next we have to change the edges. So because it's a completely different graph, I think we'll start again. I think we'll delete that. And here we'll start it off, we'll say add edge. And we're going to go from, let's go through it in order. Let's say A to B. So that's going to be 0 and 1. And we've got a weight here of 2. So just to make a note to myself, we'll put a comment there. All right. And then I'm going to copy this and modify it for the connection between A to C, which is 2. And that has a weight of 4. Okay, so that's going to be A to C, that's 4. All right. Next, let's move on to look at B's edges. So we'll say 1, 2. That also goes to 2 as well, and that's got a weighting of 1. That's A to C with a weighting of 1. Okay, next we're going to go 1, 2, 3, and that's got a weighting of 4. That's B to D. So we'll say B to D is 4. Oops, I realize I need to modify that. That needs to be B to C. Okay, and then we've got one more connection from B. That's going to E, and that has a weighting of 2. Yeah, so we're going to say B to E. Has a weighting of 2. So that should be the edges from B. What's next? C. So that's going to be 2. And that's going to E. So that's 4. Yeah, that's 4. And that's got a weighting of 3. So we're going to say C to E. It's got a weighting of 3. So we'll put that there. And that's the only connection from C. So we'll move on and go to D. D has one connection to F, so we're going to have to say, so that's going to be 3 to 5. That's got a weighting of 2, so that's going to be D to F, weighting of 2. Okay, and that's the only edge from D. Then let's go to E, which is going to be 4. And that's got 2 edges. It's going back to D, and that takes weighting of 3. So that's going to be E to D, and that's got a weighting of 3. Okay, and then we've got one more connection from E to F. So that's going to be 4 to 5, and that also takes 2. Okay, so it's going to be E to F. Okay, and I think that's it. All right, I don't actually need to display the adjacency matrix this time. Okay, so hopefully if we've added all the right edges, that should create the graph as of here. And then next we just need to call the GetPath method of Dijkstra's class to work out the shortest path. So remember, you need to include the Dijkstra class here if you haven't already. So let's set up a instance of it. I'm going to call it D. Okay, that's going to take the graph, which I think still has the handle of G. Yeah, above. Okay, and then next, because Dijkstra's GetPath algorithm returns the path in the form of a stack, we're going to need to set up a stack to store this returned value. So let's say stack 2 in my case. Let's create a pointer. Let's just give it a handle of dpath. And here's where we're going to call the GetPath method from Dijkstra's class. Okay, and then we're going to pass it the start vert in this case, and also the end vert, or perhaps you'd call it goal vert. It's one of the two. Okay, and then we just have to loop through the stack. So whilst the D path is not empty, so whilst it's false, it's here that we just want to output the, we want to call the pop method of it. Because it's a stack, we want to pop the items off the stack, and then we're going to want to get a bit more, we're going to want to get the specific information. So if you choose arrow link and then location, and then from location, you should be able to get to the name attribute there, which will give you the letters for each of these vertices. Okay, so we just want to print those to screen so we can see the path. Okay, so hopefully, if you've done this correctly, we should see the path as illustrated. Let's give it a go. And hooray, we do. Notice that we see the shortest path, as we saw in the slides, from A to B to E to F. Okay, so there you go. That's Dijkstra's algorithm for you. So why don't you guys give this a go? It's quite a complicated setup, so if you need to refer back to this video, please do. But yeah, give it a go and see how you get on. Okay, so now that we've had a look at Dijkstra's algorithm, let's move on and have a look at the second algorithm of this lecture, which is the AStar algorithm. And that's an alternative algorithm to Dijkstra for finding the shortest path between two vertices within a graph. Again, we're going to visualize how this algorithm works through an example. And we're actually going to visualize the graph differently this time. You'll see here that we've got a grid of cells, a bit like a spreadsheet or a 2D array, you could say. But here, each cell is going to represent a single vertex within a graph. And in this case, it's like a map. And you'll see that each cell or vertex has an assigned ID number in the top left-hand corner. And this is going to come in useful later when we have to keep a track of which vertices we've visited and which ones we haven't. And we've got a starting vertex, which is the blue cross, and then we've got a goal vertex, which is the yellow cross. And the aim is to find the shortest path between the two vertices. But you'll see here some of the vertices are coloured red. And in this example, that means that we can't navigate through them. So this makes the pathfinding a little bit more challenging, but it does make it more realistic, as that might resemble real-life barriers or locations that we can't visit when trying to find a path between two locations. Okay, so the AStar algorithm is going to adopt a similar approach to Dijkstra. You'll see this once we get into the code a bit later. You'll see a lot of similarities between the two algorithms. But the biggest difference, or if you like, the extension that the AStar algorithm brings is the introduction of a heuristic. And this heuristic is essentially an estimation of how far a particular vertex within the graph is away from the destination. Okay, so there are different methods for calculating a heuristic. One popular method is the Euclidean distance between two vertices, which is essentially as the crow flies, so a direct path between the two vertices, ignoring obstacles. But in our example, we're going to be ignoring obstacles, but only moving horizontally and vertically, okay, to calculate our heuristic. And it should be said that each movement between vertices is counted as one unit. Okay, so you'll see here from vertex 25 to 35, there's a total of 5 movements. We have to go through 5 vertices to get to 35. And likewise, to get from vertex 8 to 35, we have to go through 7 vertices. Okay, so that's how we're calculating the heuristic in our examples. And then we're going to go ahead and do this for every single vertex in the graph. And in this illustration, we're going to display that in the top right-hand side of each cell. Okay, remember that the top left is the ID number for each vertex. But once we've estimated these heuristic values, the main advantage is that we can incorporate them into the algorithm to discount the paths which are estimated to take longer to get to the destination, and instead focus on the paths which are estimated to get to the destination quicker. Okay, so AStar does this by adding the heuristic value, which is modeled as h, to the actual cost that it takes to get from vertex to vertex, which is modeled as g. And then it stores this in a variable called f. And quickly, we should mention that in our example, for g, horizontal and vertical movements will have a cost of 10. Okay, and therefore diagonal movements, to use Pythagoras' theorem, which if you remember, that's a squared plus b squared equals c squared. C works out to be roughly 14. So therefore the cost of moving diagonally between vertices is 14 there. Okay, and one last thing to mention before we step through the algorithm is that each vertex will have what's known as a parent pointer, which will be used to construct the path as the algorithm runs. It's the shortest path between the start and destination vertex. And in our illustration, we're going to visualize this with the orange arrow, as you can see here. Okay, so let's step through the algorithm then. Right, so the first thing we do is we assign the start vertex to be current. And then we look at all of the edges of current. And as you can see here, those are the 8 surrounding vertices. And we make the parent pointers of these vertices point towards the start, the current vertex. Okay, so that's why the orange arrows are pointing towards that start vertex. And we also place these 8 surrounding vertices within the open list. Okay, these are the currently unvisited vertices. And the only visited vertex which is our start vertex, is going to be placed in the closed list. And then we're going to examine the particular values of these 8 surrounding vertices. So we're going to look at the heuristic, which remember is the green value on the top right of each cell. And then the blue value in the top center is the actual cost, the G value. And then the red value underneath, which is center middle, is the sum of the H value and the G value. Okay, and so from there, the algorithm will focus on the lowest estimate values, which are, in this case, there's a tie. There's 2 vertices, vertex 15 and 20, which both have the estimate of 15 there. Okay, so the algorithm is going to explore both of those to work out which of the 2 is the quickest path. And in this case, it's going to start with vertex 15. And so the algorithm updates the current vertex to vertex 15. So you notice that becomes grayed out and is also placed in the closed list. And then repeats the earlier steps by working out the H, G, and F values for the surrounding edges, okay, which are, in this case, it's vertex 10 and 22. And then once it's worked out these F values, the red values for the 2 new vertices, and placed them in the open list, the algorithm then reevaluates all of the red F values for the vertices in the open list. And so as vertex 20, which you remember from the previous round, had the joint lowest value of 15, as this is now the lowest, then the algorithm then makes this vertex the current vertex and explores all of its edges. And this process is going to keep repeating until we reach the destination node, which remember that's the yellow cross in vertex 35. And then we can use the parent pointers to trace back the shortest route between the start and end vertex. Okay, so here's the pseudocode for the AStar algorithm, which again, I think it'd be better for us to explain this as we code it, as it's quite a lot to take in. Okay, so let's do that. Let's move to implementing the AStar algorithm in the exercises. And as always, I'll walk you through how to do this. Okay, so let's implement the AStar algorithm. And the good news is that we've already done most of the groundwork. We've got the graph set up from the previous exercise where we implemented Dijkstra's algorithm. We've also got the node class, and the AStar algorithm itself is going to be very similar to Dijkstra's algorithm, but just include a few extensions. Okay, so hopefully this exercise won't take as long as the last one. All right, so let's walk you through the modifications we've got to make in order to implement AStar. Okay, so starting with the node class, we need to add an F attribute and a H attribute. Okay, remember from the slides, the H is going to represent the heuristic, and which we're going to add that to the G value to create the F value. Okay, so we need to add in float attributes for F and H. Okay, and the good news is that everything else, the methods should be the same. Oh, the only thing we do have to do is initialize these attributes. So in the constructor, let's just write that H is 0 and F is 0. Okay, so that should be it for the node class. That's good. So let's move on and have a look at the AStar class then, which again, you should notice quite a lot of similarities between this UML diagram and the implementation of Dijkstra. Okay, so what I suggest doing actually is copying this class. And I've already created a template for AStar. So what I'll do is I will copy just the methods and the attributes. I may also, it's probably best to include those references as well, actually. So let's go to the AStar, put that there. And I've already got them. That's good. If you haven't done that already, just copy these include statements over, because we're going to be needing them as well here. Okay, and the key differences to point out is remember that the AStar algorithm also maintains a closed list in addition to the open list. Okay, and this is going to be implemented as another linked list. Okay, so let's copy the attribute for open and then make one for closed. Okay, and the only extra method is the getHeuristic. Okay, and we're actually provided with that, which is helpful here. So let's add that in. Okay. We're going to make a few modifications as well. So let's change the constructor to match the class name. Okay, AStar. And we also, whilst we're in the constructor, we'll also need to implement the closed linked list. That's going to be the same as the open one. So it's going to be of node type. And then call the constructor. Okay, so that's that. We've just added the getHeuristic. We've got the reconstruct plan, and we've also got find lowest node. Okay, so we should have done that. And then I think we get to the GetPath. Oh, actually, just before we get to implement the GetPath, which will be different actually, we're going to have to modify this a little bit, but we can use this as a starting place, which is good. But coming back to exercise 7, we will need to add in these coordinates here. And if you remember way back to the start of the previous lecture on graphs, we added those x and y attributes, which we didn't do anything with at the time. If you remember, we had, where are they? They'll be in the location class. Remember we added these, and we set them to 0, and in the one of the non-default constructors, and then in the other non-default constructor, we're actually going to assign the parameters to them. Okay, but we never did anything with them back then. Okay, but now we're going to, because we're going to assign coordinates for each of the vertices based upon their position within the graph. So if we were to go back up to the graph representation here, we're going to be using the x-axis, which is the horizontal axis, and the y-axis here, Okay, so 0 values will be at the bottom of the y-axis, and then 1 will be in the middle, and then 2 will be at the top. And likewise for the x-axis, 0 is going to be furthest left, and then we've got 1, 2, and 3. Okay, so we have to go back to the main and modify the add vertex statements to include these x and y values. Okay, and we're actually given some of them to start with. Here we go. So A is going to be at the x position of 0, because remember it's furthest left, and then y of 1, because it's in the middle there. Okay, and then for D, we're given 2 and 2. All right, so I'm just going to add them in so I can move back to the graph representation. So let's go back in here, and we're going to work the others out. Okay, so for A was 0 because that's furthest left on the x horizontal axis, and it was 1 because it was 1 up from the bottom on the y-axis. So B is have an x value of 1 and should have a y value of 2. All right, so let's modify that. Will I say x1, y2? Okay. C is going to have an x value of 1, y value of 0 because it's on the bottom, remember. For D, we've already added that. That's 2 in from the left and then 2 up from the bottom. E is going to be 2 in from the left, but 0 for the bottom. And then F is going to have an x value of 3 from the left, and then it's in the middle, so it's going to have 1 there. Okay. I should also say that you could create a copy of this graph if you wanted to maintain the previous code to work with Dijkstra, but just here to save time, I'm going to modify the previous graph. Okay, so do whatever's best in your circumstance, but here we've modified the original graph to work with AStar. Okay, it should still work with Dijkstra, actually, it should be said, but just if you wanted to keep the two graph implementations separate, it's probably best just to create a copy of that. Okay, but that should solve exercise 7 there. We've added the positions to then work out the heuristic. Remember, the heuristic is the estimate for how far away each vertex is from the goal vertex. So that's what's going to be used to calculate the h value. Okay, and now here we go. We're going to come to the GetPath algorithm. And if you haven't already, you can get this from the PowerPoint, the slides. Okay, so just make a copy of this. And as always, I'm putting it into Word just so I can have a copy on my left-hand side to then implement in the right-hand side. Okay, in the Visual Studio. And as I said, the good news is that it does follow a very similar pattern to Dijkstra's algorithm. So that's why I recommended copying the GetPath from Dijkstra's algorithm. And we're just going to go by, I'm just going to go through it and modify it line by line. Okay, so you'll notice here that the first 3 lines should be the same. Wrap start and goal in nodes, which we've got. And then we want to insert the start node into the open list, which we've got. So those 3 lines are good. And then whilst open is not empty, that's good. We can use that. And then into the loop, set current to the lowest node in open. That should be the same. That's not a problem. And next, remove current from open. That should also be the same. We want to delete it from the open list. And then here, I've emboldened some of the modifications that we're going to have to make. So here, made a note that we're going to have to modify this line. Okay, and we actually want to change it from a linked list. We want to maintain a priority queue here. So I'm going to modify that. It's still going to be of location type, but here's where we're going to write priority queue. Okay, and we'll also going to want to call the non-linked list version of a get adjacent vertices. Remember, we had two. We had one which works with a priority queue and one which works with a linked list. Here's where we want to call the non-linked list version. Okay, the original one which we created way back in the previous lecture when we first implemented the graph. Okay, and the parameters should be the same. We want the current location. Yeah. Okay, so that's good. That's that one. Let's move on to the next line then. So whilst adjacent not empty, yeah, that looks good. That should be the same. All right. So then let's move on to the next line, which is set edge to remove vertex in the adjacent priority list. Okay, so this looks to be a little bit different. Rather than getting the lowest weight, what we can do is we can call the remove method of the adjacent vertices list. Okay, so I'm going to replace that second half from the assignment operator with adjacent vertices and then call the remove method. Okay, so that should have modified that line there. And then we want to wrap edge in node. Okay, that's the same. We can keep that. And then next line, we haven't got anything to do with distance because we're actually going to calculate that using the heuristic. So that's going to come a little bit later. Next, we're advised to set edge node parent to current. Okay, I think we've already got this. I think we've done this. Oh yeah, here. So if you want to cut this line from within the if statement and pop it underneath the edge and edge node pointers, pop that there, and that'll take care of that. And then next we've got this if statement, which we've actually already got here. So let's also cut this and pop it above. All right, so that's that bit. If we're at the goal, then we want to return the reconstruct plan. So that's the same, but we've just moved it up a bit. And then next, here's where we calculate the G, F, and H values. Okay, so rather than maintaining a attribute for distance, we're going to be using the H value. So we can actually remove that. And what we'll do is we'll say edge nodes G is going to be the current G plus the distance between the vertices of current and edge, which should be the same as Dijkstra's algorithm. Yeah, we've got those two there, so that's fine. And then next, we're going to come to that a bit later. But next, we're instructed to work out H. Okay, so we'll say edge node H equals get heuristic. Okay, so this is the method which we added. That's new here for the AStar algorithm. All right, and that's going to take the edge parameter and the goal. Okay, I want to pass those two to that. Okay, and then finally, we want to add the two together. So here's what we're going to say. Edge node F equals, we're going to have to refer to G and H through edge node. Okay, so we have to say edge node point towards G plus edge node point towards H. Okay, and then that should work out the F value, which remember that's the sum of G and H there. Okay. All right, so that's that bit. Those are those new lines there. Okay, so after we've done this, we then want to find edge node in the open list. So if we call find through open, we should be able to search for add node. Okay, and because that's going to return a node pointer, we want to store that. So let's say, we're told here it's found in open. Okay. All right, that's that line. And then next we come to the comparisons. This is where we want to test these things. So first one is if found in open, and those two chevrons pointing away from each other, the less than and the greater than, that's an alternative for not equal to. Okay, I mean, you could do the and operators if you want. You could say less than and greater than, but just to save time, we'll say not equal to 0, and that's going to be the two ampersands. Found in opens f is less than edge nodes f. Here's where we're going to want to say skip to the next adjacent iteration. Okay, so the easiest way to do this is just to say continue to go on to the next iteration. All right, so that's that bit. And then what we've got next, we've got end if and then set found in closed to be find edge node in closed list. Okay, so that should follow a very similar format to this. So let's copy that, pop that here. All right, but rather than found in open, we're going to want to say found in closed and then refer to the closed list there. Okay, so that should be that line. And then next, we can actually copy this if statement, and because we're going to do something very similar, except change it to found in closed. So let's modify this. Rather than found in open, we're going to say found in closed. And here we'll say found in closed 2. All right, and that's also going to want to skip on to the next adjacent iteration. So we'll have a continue statement there. All right, and as those are the last if statements, we'll remove this as we don't need that. Okay, and then we want to insert edge node into open, which we're doing here. That's the same from Dijkstra's algorithm. Okay, and we're not actually going to be deleting it from the adjacency list, so that's take that out. And then underneath that inmost while statement, we want to insert current into closed. Okay, so we're going to say closed, call the insert method, and then say current there. Okay, so that should be it for the AStar algorithm. All right, so hopefully if we've implemented it correctly, let's go back to the main and let's get up and running. Okay, so you're going to want to include the AStar class if you haven't already. And let's use the graph from the first exercise, Dijkstra's algorithm. And actually the AStar algorithm is going to follow a very similar format to Dijkstra's, so I'll use this as a template. But what I probably will do is just comment this out. It shouldn't interfere, but just to be on the safe side. And then again, so let's modify this template. Rather than making an instance of Dijkstra, I want to make an instance of the AStar. Let's call it A. And again, let's modify reference to Dijkstra to make reference to AStar. All right, and the GetPath is going to return a stack. So let's call this A path, and then also modify that to be the A pointer, and then modify these final references to a D path to make them A path, and then that should follow the same format as before. So let's try running it, and hopefully we should see the same path. Hooray, and we do. That's good news. Okay, so There we go. That's AStar successfully implemented. Why don't you guys give it a go? Again, it's if you've done the groundwork from the first few exercises, it shouldn't be too many modifications. But if you need to go back and check the video at any point, please do. And yeah, see how you get on.